All right, so now that we've talked about what one-to-one is, what we need to understand is that in order for a function to have an inverse, it has to be one-to-one. A function that is not one-to-one will not have an inverse. So that's the first thing, is that a function has to be one-to-one to be able to have an inverse. Now, before we get involved in what an inverse is and how to find one, I want to show you the notation for an inverse function. We already know that f of x, that's the notation for just a normal function. We know that. We've been dealing with that now since chapter 1. Well, the inverse function, its notation looks like this right here. Where it looks like a power of -1, it is not a power, it is not an exponent. We actually read this as f inverse of x, and this is the notation we use for inverse function. So it's just a notation thing there, but we read it as f inverse of x. Now, let's talk about these inverse functions. I like to name this gray box the first of several interesting facts. So this is interesting fact number 1. If I have a function that's one-to-one, then another function, in this case we'll call it g, is an inverse of my original function f if the following happens. If f of g of x equals x, and if g of f is equal to x. Both of these have to happen at the same time. So interesting fact number 1, f of g has to equal x, g of f has to equal x. If that happens, then my function has the inverse. And the inverse is g. F and g are inverses of each other. All right, so let me go ahead and unhide this here. The condition that f is one-to-one in the definition is essential. So I already mentioned this. In order to have an inverse, there has to be, my function has to be one-to-one. All right, let's talk about some more interesting facts. The first one is not so interesting, quite frankly. If my original function is one-to-one, then my inverse exists. That one's not so interesting. The next few are even more interesting, though. So, number 2, interesting fact. The domain of the original is going to be the range of the inverse. And the range of the original will be the domain of the inverse. Okay, so domain of the original is the range of the inverse. The range of the original is the domain of the inverse. My domains and ranges are trading. Interesting fact number 3. If the point, the coordinate, AB, lies on the graph of the original function, then the coordinate BA lies on the graph of the inverse. So I call this one interesting fact number 2. I call this one interesting fact number 3, or you could even say 3A. And then the next sentence down here, this is my next interesting fact. I really would have broken these up had I been the one writing these notes. And so it says that the graphs of the original function and the inverse function are going to be reflections of each other or symmetric about the y equals x line. Okay, so the graphs of the original and the inverse are symmetric about the line y equals x. And then last but not least, interesting fact here, number 4. If I want to find the equation for the inverse, the way I'm going to do that, first of all, remember that f of x is the same thing as y. Interchange or trade x and y, solve for the new y, and this is going to give you your inverse. We'll go through those step by step. So for example number 3, it says that we should decide whether these two functions are inverses of each other. So we're going to use interesting fact number 1, where we're going to test by using composition whether f of g is the same thing as g of x, and they should both be equal to x. So let's go ahead then, and we'll find f of g first. We want to know, does this equal x? So we go ahead and we take g of x out and replace it with what it equals. We found that over here. And then we'll go to our f function, and wherever we see an x in our f function, we'll replace it with this guy right here. All right, so this is going to look like 2 times that ugly statement right up above, 1/2 x minus 5, and then plus 5. All right, so let's do a little bit of distribution there. 2 times 1/2 x is going to give me x. 2 times -5 is going to give me -10. And then I'm going to just copy down my plus 5. And I notice here that this is equal to x minus 5. Unfortunately, this is not what we want. We want f of g to equal x, not x minus 5. So I can immediately say right now, f and g are not, sorry, I went too far. F and g are not inverses of each other. In fact, I don't even have to keep on testing because I can tell by the first part of the test, no, they're not inverses of each other. Now, what would I have done if it did work out? Like maybe at this step right here, I came up with something like x minus 10 plus 10. This is equal to x. Well, if that's what happened, then I would go back up to the top and I would say, all right, now I need to test, I need to test g of f of x. And I would run that test and make sure it also equals x at the bottom. But that's not what happened in this case. So we're going to delete that and go to the next example. So this is just a repeat, something that we've already said. By definition, the inverse function, by definition of the inverse, the domain of the original is going to be the range of the inverse. And the range of the original will be the domain of the inverse. All right, example number 4 says to find the inverse of each function that is 1-to-1. So really, this is a 2-part question. The first thing is find out, find out if it's 1-to-1, and if it is 1-to-1, then secondly, let's go find the inverse. Okay, so we look at part A, and remember one of the definitions I gave you for 1-to-1 is that there's no y repeats. So when you look at your y values, none of them are repeated y values. So we can say with certainty, yes, this function is 1-to-1. So then I need to do the second step and I need to find the inverse. Well, let's go back and let's use interesting fact number 3, where if the coordinate AB is in the original, then the coordinate BA will be in the inverse. So in order to find the inverse function, notice that the notation here that I'm using is F inverse is equal to, and I'm going to take each coordinate and just trade the x and the y values. So -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. So that's part A. Now let's look at part B. Do I have any y repeats? Well, yes, I do have y repeats. So it's not 1-to-1, and if it's not 1-to-1, there's no sense in finding the inverse because only 1-to-1 functions have an inverse. All right, the equations of inverses. The inverse is found by trading the x and the y values in our ordered pairs. The inverse function is going to be found the same way, so let's look at some steps here. If I want to find the equation of an inverse, then the first thing I'm going to do is just mentally replace f of x with y. Okay, so that's the first thing. We already know that f of x is the same thing as y, so that's no big deal. Replace x with y. F of x with y. Step 1 is going to be to trade your x and your y values. This goes back to interesting fact number 3. All right, after you trade your x and your y values, solve for the new y. And after you've done that, take out the new y and replace it with the correct notation of f inverse. Now, I do want to point out here that any restrictions on X and Y need to be considered, and we'll run into that here in just a moment. All right, so let's find the equations of some inverses. So the directions say that we should figure out, first of all, is it 1-to-1? And if it is 1-to-1, we should find the equation. So the first thing I want to ask you is, can you think of what this graph looks like? Well, hopefully your brain is thinking that this is the parent V graph. Well, the parent V graph does not pass the horizontal line test, so it's not 1-to-1. All right, let's go over to letter B. Letter B, this is 1-to-1 because it's just a line, and lines are 1-to-1. They meet the horizontal line test unless it's a horizontal line to begin with. All right, so let's follow our steps. Step number 1 says to trade the X and the Y's. So my Y became an X, my X became a Y. Step number 2 says to solve for the new Y. So you're going to add 7, and then you'll either divide by 4 or multiply both sides by 1/4. It's the same thing. And then step number 3 says you can't leave that new Y written like that. You need to use the proper notation. And so my proper notation is going to be, in this case, it started out as a g of x. So this is going to be g inverse of x is equal to 1/4 times the quantity x plus 7. All right, for letter C, is it 1-to-1? Well, this is one of our parents. So this is just, remember, the cubing parent, and it's moved up 5 units. So yes, it is completely increasing. It passes the horizontal line test. So yes, this is 1-to-1. So let's find the inverse. So step number 1, let's trade X and Y. Step number 2, let's solve for the new Y. This is a 2-part step here. So I subtracted 5 on both sides, and now I need to take the cube root of both sides. And then the last thing is you can't leave it as y equals. You need to make sure that you replace that y with, in this case, h inverse, because it started out being an h of x function. All right, example number 6. This one's going to be a little bit more challenging than the last few were. But we're going to work it the exact same way. So let's go ahead then. And for the very first step, let's go ahead and trade our x's and our y's. Don't forget that you need to include the restriction in this. All right, so all of the x's and the y's need to be traded. And if you are wondering why I said that, that goes back up to this highlighted area. Any restrictions on x and y need to be considered. Okay, so that's first. All right, secondly, we need to solve for the new y. Well, the problem here is that I have more than one y, so which one do I solve for? Well, what we're going to do is we're going to think of this as a fraction equals a fraction, and we're going to use cross multiplying. So we're going to multiply these, and we'll multiply these, just like we would have done back in Algebra 1. All right, so cross multiplying. Oh, I erased the wrong side there. Sorry about that. So I went ahead and used distribution when I did this. So x times y minus 5 times x. Now, if you'll notice, ask yourself, how many terms are in this equation? Hopefully you answered 4. Some of those terms have y's in them. So what we want to do is we want to get all the terms that have y in them on one side of the equal sign, and all the terms that don't have y in them, let's get to the other side. So I'm going to move this guy here to the left. And you'll notice I also moved that negative 5x over to the right. All right, well now I have the occasion where I have a GCF of y. So let's factor out the y GCF. And all of a sudden, I now just have a single y that I'm able to solve for. So let's divide on both sides by x plus 3. Of course, we can't leave it like this because our last step says that we should rewrite with our inverse notation. And so this is going to be f inverse is equal to 5x plus 1 over x plus 3. All right, now, you can't leave it like this. Remember, we had restrictions. So all the way up here, our restrictions dealt with whatever made a 0 on bottom. And we need to do the same thing down here and ask yourself, well, what is it that will make a 0 on bottom? So therefore, our restriction is that x cannot equal -3. All right, now how do I graph the inverse of a function? Okay, so step number 1, find some ordered pairs on the original function. Step number 2, trade the x's and the y's to find some points on the inverse graph. And then step number 3, plot. Plot your points. This next line here, again, this is something that is repeated. We can find the inverse from the original just by locating the mirror image of each point with respect to the line y equals x, or x equals y, same thing. So once again, my y equals x line should be the mirror that reflects the two functions. The example 7 here says determine whether our functions f and g are inverses of each other. Now, I got to tell you, yeah, they are about the x-axis, but they are not symmetric about the y equals x line. So, in other words, this here is my mirror, but my mirror needs to be the dashed line here. Okay, so essentially we would say, no, these are not inverses of each other because of the fact that they're symmetric about the wrong line. If we go to the next part though, this time we actually have to graph the one-to-one function. We have to graph the inverse, excuse me. And so I have marked my points here, but let's use interesting fact number 3. And so the coordinate -4, 0 is going to be graphed on 0, -4. The coordinate 3, 1 is going to be graphed at 1, 3. And so then all I have to do is connect the dots. And when I do that, I think you're going to actually notice here that these are symmetric about the y equals x line. My y equals x line is a mirror between the two graphs, between the two lines. All right, let's do that to this one over here. So I've actually marked, there's the 3 points, 0, 0, 1, 1, and 2, 4. And so when I trade 0, 0, I get the same spot. When I trade 1, 1, I get the same spot. But then when I trade the 2, 4, I'm going to be graphing at the coordinate 4, 2. So when I look at this then, it's going to look something like this. Now, I want to camp out here for just a moment. If you look at this original graph, this looks a whole lot like half of the squaring function. And it has the same coordinates as the right side of the squaring function. When you think about what undoes squaring, we would say that the square root undoes squaring. Well, here's something kind of cool. An inverse is just simply the undo button. So if you want, you know that squaring undoes square rooting. Adding undoes subtracting. If you want to undo a function, you're going to use its inverse to undo it. So inverses are the same thing as an undo button. And so it kind of shows you on this graph that my squaring function, or at least half of it, and my square rooting function are inverses of each other. They are actually undoing each other. All right, example number 8. So again, we are looking here for the inverse. So the first thing that we want to do is go ahead and trade our x's and our y's. Notice you do have a restriction that you need to worry about. If you think about what this graph looks like, this is a parent parabola that's moved up 4 units. I actually drew it down here at the bottom. And the reason the right-hand side of it is dashed is because my restriction says I'm only using x's on the left side. I'm only using x's that are less than or equal to 0. So these are the x's that I'm using. I'm not using x's that are greater than 0. So I'm only drawing half of the parabola. So we also have to have this restriction here that says y is less than or equal to 0. All right, so let's go ahead and solve for the new y. So we're going to subtract 4 on both sides. And you remember that in order to undo a square, we need to square root both sides. But don't forget, when you square root both sides, you have to remember that there's a plus minus, pos neg. But let's go back to this restriction. This restriction said that my y should be less than or equal to 0. So in our pos neg then, we're only going to keep the one that's less than 0. So we're going to keep the negative one. And in the same step here, I also went ahead and changed my notation over to inverse notation. Okay. Now, I don't remember what's under here. Yes. So we also have to remember that this guy has to have a restriction, because remember that anything inside the square root has to be greater than or equal to 0. You can't have negatives under the square root. So then x minus 4 is greater than or equal to 0. And so the restriction then gets carried down here. I wanted to point out really quickly that domains and ranges can be traded. And so here, it's pretty easy to see that the domain of the original was that restricted version. The range of my original was going to be, if I had graphed it, and you can tell this on my graph, my range is from 4 up to positive infinity. Well, remember that the interesting fact says that domains and ranges are traded. So then that means the domain of the inverse is going to be from 4 to infinity, and the range of the inverse is going to be from negative infinity to 0. And again, you can see here that they are just simply trading according to interesting fact number 2. All right, the example 9, I'm actually not going to show on the video. This is not something that's part of our course. We do not have it assigned for any quizzes, nor will it be assigned on a test. This was just something that was going to be for fun if we had some extra time. And I think you and I will agree that we don't have any extra time this semester. So this is just going to be something free. You can take a look at this in the textbook if you'd like and figure it out. It is just something kind of cool. So